Okay, welcome back. Now we're going to go on to chapter 5, section 3. Logarithmic functions and their graphs. So basically, you heard the word before, logarithms, like log or natural log or ln. Logarithmic functions are the inverse of the exponential function. Right, so the connection between the two is just a very straightforward. I'm going to go ahead and show you this, the transformation, because we'll be using it for the rest of this chapter. Okay, logarithmic equations, we abbreviate it as log. This is how we abbreviate logarithmic functions. This is read log base A of x equals y. What it means is the power that you raise A to get x. The power y that you raise A to get x. Now, what do these mean? So what this means is this is called the base. When we convert it from logarithmic to exponentials, because since we're talking powers, we're talking about exponentials. So the base comes over here and pushes up that one. When the base is gone, the log falls off. So on this side, all we have left is x, a to the power y. So there's the conversion from logarithms to exponentials. So the log base a of x equals y, x equals a to the power y. So let's just practice converting these. So let's say I had log base 2 of x equals 3. We don't know what x is, so let's convert this to exponentials. Remember, the 2 comes over here, picks up the 3. The log falls off, so we have x. So 2 to the third is 8. That means 2 to the power 3 equals 8. That's what it tells us. And they're inverses of each other. All right, so that's what we're looking at. Since they're inverses of each other, remember, since they're inverses of each other, remember what the graphs have to do? They have to be perfect flips across this line. Since the e to the power, or x, the exponential equation a to the power x is that equation, that graph, we have to be able to flip it across this line, which means it crosses, instead of at 0, 1, it crosses at 1, 0. This is the log base A of x. So they're inverses of each other. All right, let's see, we've got some examples here. Example 1. Yeah, we did that. So example 2. Find each of the following. So A, we have log base 10 of 10,000. B, we have log base 10 of 0.01. Log base 2 of 8. Log base 9 of 3. Log base 6 of 1. And log base 8 of 8. All right, so let's look at the first one. So we don't know what these equal. Or we say y. Let's convert this to exponentials. So it becomes 10 to the power y equals 10,000. What we have to do here is we have to try to make the bases the same. So 10 to the power y, what is 10,000 made up of? So it's 10 to the power 4. Since the bases are the same, that means y is equal to 4. That means the answer to this equation is 4. If the bases are the same, then the exponents have to be the same. If the exponents are the same, that means the bases have to be the same. Do the next one. Yeah, same thing. That's why. So 10 to the power y is equal to 0.01. This is, anytime you move decimals, just a power of 10 or something. Since you moved it to the left, it moved 2 spaces to the left. It's -2. So since the bases are the same, y equals -2. So 2 to the power y equals 8. 8 is 2 times 4. 8 is 2 times 2 times 2, which is 2 to the power 3. Since the bases are the same, y equals 3. So 9 to the power y is equal to 3. What is 9 made up of? 9 is made up of 3 squared. Power to a power you multiply. So it's 3 to the power 2y equals 3 to the power 1. Since the bases are the same, we know that 2y has to equal 1. So y is equal to 1/2. We have 6 to the power y equals 1. The only way 6 to the power of anything can equal 1 is if y is equal to 0. That's the answer there. These next two, yeah, these are going to be pretty important ones. So we have 8 to the power y equals 8. 8 has a power 1. Since the bases are the same, that means y equals 1. These two have properties named after them, but so the first one says log anything of 1 is always going to be 0. Log anything of itself always equals 1. So remember that when we convert from logarithm to exponents, the base comes over here, pushes up the y. The base is gone, so the log falls off, and that equals x by itself. So this is the conversion equation we'll use. Let's convert all of these. 16 equals 2 to the power x. So this is our x value. This is a, and our y is x. The base remains the base, and we just switch the 2 here. So it's 16 equals x. So here we have 2 to the power x equals 16. 2 to the power x. So the y value is x, and x is 16. So this is the conversion. Log base a of q is equal to 8. Oop, no, that's the wrong section. 10 to the power negative 3 equals 0.001. So this is a, this is y, and this is x. So log base a is 10 of x is 0.001 equals y, negative 3. And there's the conversion. And c is e to the t is equal to 70. So this is a, this is y, and this is x. So we have log base e of x equals y. And there's your answer there. Now let's go from the other way. Let's go from logs to exponents. So I give you log base 2 of 32 equals 5. The 2 comes in here, so it's 2 to the 5th. The log drops off, equals 32. Log base A of Q equals 8. The base pushes up the answer. The log drops off. We just have a Q. So we have X equals log base 2 of M. The base comes over here, pushes that one up. The log disappears. There. Example 5 deals with finding logarithms using a calculator. So we have the log 645,778. So A is the log of 645,778. And then B is the log of 0.0000239. And the log of -3. And well, the next thing we're going to talk about is your calculator only has 2 log buttons. Your calculator only has the log or the something called ln. And there's a reason for those. So that's why just find the log button, press it, type in this number, and there you have it. Same thing with all these. You're going to find out that this one's going to be difficult because you can never have a negative, take a log of a negative number. Because let's look at the example. Log base A of -3 equals X. So that becomes A to the power X equals -3. The base is a positive number. There's no way a positive number can turn into a negative number. So this one, you cannot take a log of a negative number. Remember the formula? The domain is in here. The graph always looks like this. You can only use X has to be greater than 0. You cannot have a negative number here. Y can be anywhere from positive to negative infinity. But this number here can never be negative or 0. Likewise, in example 6 on your calculator, ln 645,778 ln 0.0000239 ln of -5 ln of E and ln of 1. This will give you some number. Just type it in the calculator, it'll give you some number. Same with this one. This one, again, you cannot have an X in here. This one does not exist. because you cannot take a negative. This one will equal 1, and this one will equal 0. Remember, we said earlier, the log of 1 is always 0. So also the natural log of 1 is 0. So we also had this, in logs. There's log base A of A is equal to 1. Now with ln of E equals 1. These are your 4 rules that you go by. Let me tell you why. Three types of bases for logs. And depending on the base, that depends on what the function is. We have base 10, base E, Euler's number, and base A, where A does not equal 10 or E. It could be anything else. If it's base 10, we call that a common log. The reason it's called a common log is because our numeric system is a base 10 number system. So if you have a logarithm base 10, because it's common, you don't have to put that 10 down there. So if there's nothing down there, it's automatically a base 10. And that's what you'll see in the calculator. Base E is called a natural log. So if you have a log base E, we rewrite that as ln. So if you ever see an ln, that's a log base E. And then anything else is just log base A of X equals Y. As long as A is not 10 or E, it's anything else. And that's why these two are the most commonly used, and that's why you'll always see them on calculators. So these are pretty. So the question you should have, if I gave you log of 10, you get 1. I see, put in a calculator, you'll get that. Same thing with ln of 1, you get 0. Again, you can type that in your calculator, and that's what you get. But what if I asked you to do log base 3 of 5? What does that equal? There's no key on the calculator to do that for you. So to find this one, to find the value of log base A of X, we need to use the change of base formula. The change of base formula is this. Because remember, our calculators only have log base 10 or log base E, nothing else. So now if we have this, we can use there's 2 of them we can use. we can use the common logs, or we can use the natural log. It's the same ratio. This number will go on top. This base will go on the bottom. It'll always give you the right answer then. All right, so let's see, you have example 7, 8. So it's log base 3 of 8. Oh, yeah, so it's saying log base 3 of 8. And then example 8 is the log base 3 of 8. But this one says use the base 10. And this one, use the base E. So this one is going to be log of 8 over log of 3. This one's going to be ln of 8 over ln of 3. That's all there is to it. The graphs of log x and ln x are pretty much the same. This is examples 10 or 9 and 10. They'll all have the basic shape of that. All right, so the only thing different is the speed in which it changes. Let's look at graphing the shifts of them. This is example 11. So f of x equals ln of x plus 3. B equals f of x equals 3 minus 1/2 ln x. And C equals the absolute value of ln x minus 1. Yeah, we know what the ln function looks like. It looks like that. It goes crosses through 1. But this is a horizontal shift because it happens inside the function. So this one shifts 1, 2, 3. It shifts back to -3. And the graph, it used to graph through here. So now, since this is our new y-axis, it still graphs through that one. So -1, that's -2, and that's -3. So it just shifts back 3 spaces. There's ln x. 1/2 makes it grow a lot slower. This, since it's outside the function, so this is ln x, this is 1/2 ln x. This one's going to be -1/2 ln x. Since it's outside, I got to flip the graph, flip it across the x-axis. And then this is the vertical shift. One, two, three. So that's what it looks like. Again, it's the same thing we did in transformations. here's our function. If it's inside, it's a horizontal shift. If it's outside, nothing to do with the x, it's a vertical shift. If it's a coefficient, then it is a vertical, either a squash or extension. And then the x and negative in front changes across the x-axis. So here's the original ln x. It crosses at 1. X minus 1 equals 0. So it moves the, so ln x minus 1, it shifts the x-axis, the y-axis. So that's 1. Now it crosses at 2. It used to cross at 1. So since that's new. Now what it says here is the absolute value. That means I can't have any negatives. That means all of these that come down here are switched to those. That's what it looks like. Right. So that does it with that section. It's a little after 11. Let's call it a day. We'll finish up chapter 5 and chapter 6 next time. Because we only have, now we have the properties left, and solving equations. And those are the easy ones. So we have 2 more sections in chapter 5, and then 1 section or 2 sections in chapter 6, and we're done.